All right, so today we're going to look at the second half of the unit. We're going to revisit this whole solving exponential equations later on in the unit, because it turns out that in order for you to solve exponential equations algebraically, if a common base is not possible, then you have to use logarithms as a tool. So today is a very brief introduction to logarithms. There are two main things that you need to understand here in this unit. And one is the relationship between a logarithmic and an exponential function. They are inverses of each other. But the other one, and this is different, is writing a logarithmic expression in exponential form or vice versa. So when I look at what's highlighted in blue, just out of the gate, I want you to think about what I'm telling you. When I look at what I'm highlighting in blue, this logarithmic function and this exponential function are two different things that are inverses of each other. But when I look at what's highlighted in green, I'm saying there is a thing that you can write with exponential language or logarithmic language, and it means the same thing. What I've highlighted in green is very much similar to translating bonjour to hello or hello to bonjour. Did I pronounce that okay? Oh, not bad. They mean the same thing. It's just a different language. And then we're going to be using this part that I've highlighted in green to evaluate logarithmic expressions. So to begin with, we define a logarithmic function as the inverse of an exponential function. This inverse is the same thing we learned about in Unit 1. You switch x and y, and you get an inverse. So I want to do a bit of review here with you in terms of inverses of functions. To take an illustration here, and remember, you swap x and y to get an inverse. This is a function. Y equals 2x minus 6 is one of the simplest functions you could talk about in high school math. It's a linear function. If I said to you back in Unit 1, what is the inverse of this, you would write that. Is it clear that these two things are not the same? They're not. They're different. They are inverses of each other. They mean different things. They have different graphs. But when you swap x and y, and you should remember this, for the diploma exam you have to rearrange for y. And rearranging this equation for y is like stealing candy from a tired baby. You just take it. It's easy, right? You add 6 to both sides and divide everything by 2, and you get y equals 1/2 x plus 3. Correct? Okay. Do you agree that at some point in the history of mathematics, somebody had to invent the concept of dividing? So if you were in a math class back in the Stone Age days and they were teaching you math, but you didn't have a concept of dividing, all you could do was say 2y equals x plus 6, and you would just stop there. So somebody had to introduce this idea of dividing to finish this rearranging. That's a linear function. It turns out the inverse of a linear function is a linear function. Okay. What about if I had this function, which is a quadratic function, y equals x squared, and I swap x and y, these are inverses of each other. How do you rearrange for y? Well, I hope you understand that somebody introduced the concept of a square root at some point in mathematics. Before the concept of square rooting, you couldn't communicate on paper what we meant by this inverse. But you take the square root, and for reasons that I don't really care to review, you have to go plus or minus. And what we end up with is a quadratic function that has an inverse, and the inverse is two square root functions. Root x, which looks like this, and negative root x, which looks like that. It's two different functions put together as one, which means the whole thing is not a function because it would fail the vertical line test. Are you still with me? Okay. So what if we take a look at this exponential function? Y is equal to 2 to the x. And I say, well, what's the inverse of it? Well, that's easy. You swap x and y. So here's the exponential function on the left, y equals 2x, and on the right is its inverse. And remember, inverses are inverses of each other. So my point right now is just this. Y equals 2 to the x is the inverse of x equals 2 to the y, and x equals 2 to the y is the inverse of y equals 2 to the x. They're inverses of each other. Now, if I say to you, rearrange that equation for y, rearrange this equation on the right for y, you just give me that look that's on your face right now, which is, I don't know what to do. You were in the same position as somebody who didn't learn about square roots would be in when they try to rearrange this equation for y. You have to be shown that there's a bunch of squiggles on paper that mean rearranging for y in this context. And it turns out that when you rearrange this for y, you write that. These are not inverses of each other. This x equals 2 to the y is the inverse of y equals 2 to the x. But x equals 2 to the y can be rearranged for y by writing what I have on the right. And it's pronounced y equals, there's lots of ways to pronounce it, but one of the ways is to say y equals the base 2 logarithm of x. What does that mean? What does y equals the base 2 logarithm of x mean? It means x equals 2 to the y. All right? And this on the left can be thought of as hello, and on the right can be thought of as bonjour. You need to be able to translate from one of these forms to the other. And I want to point out to you that I might be getting a little ahead of myself, but this expression on the left is called the exponential form of the statement. The expression on the right is called the logarithmic form of the statement, but they mean the same thing. I want you to notice that there is, I call this the base 2 logarithm. There is a base on the logarithm, and there is a base on the exponential, but the base is the same. The difference is, when you look at what's by itself in the exponential form, it's the opposite item that's by itself in the logarithmic. And you need to be able to convert back and forth. Okay? So, I'm going to give you some details about this. Since everybody, this right here, this thing, is the inverse of y equals 2 to the x. And by the way, the thing on the left is the inverse of y equals 2 to the x. And we have rules about the base. We're going to have rules about the base, whether it's written in logarithmic or exponential. Okay? If the inverse of y equals 2 to the x is x equals 2 to the y, then the base of a logarithmic is the same as the base of the exponential, that is the inverse. But we have rules about bases. Bases can't be negative. Bases can't be 0. Bases can't be 1. So, that is why I am telling you here that the base is not 0 and not 1, but it's greater than, it's a positive number. When I say c is greater than 0, do you understand I'm telling you c can't be 0? Okay, so it has to be a number bigger than 0, but it can't be 1. Now, why am I saying x is greater than 0? Well, when you look here, x is calculated by taking 2 raised to a number. And 2 is a positive base, and a positive base raised to any number will always give you a positive result. You can never get 0. You can't raise 2 to a number and get 0. And this is tricky, I know. But since this x here must be positive, and x equals 2 to the y is the same as y equals log base 2 of x, what this means is this number has to be greater than 0. You cannot take the logarithm of 0, and you cannot take the logarithm of a negative. You don't understand everything in detail yet, but if you take your calculator, you have a log key. It's a special log key. And if I take log of 0, I get smacked across the head. I'm told, no, you can't do that. If I take log of a negative number, again, I'm told you can't do that. But if I take log of 85 and get, I take log of 85 and get 1.29, whatever that means. I can explain it in a second. That's allowed. No, I'm not going to explain it because then I have to get into something else. We'll leave the reasoning for that in a second. So that's the rule for a logarithmic function. This up here that I'm going to highlight, and I'm going to run out of colors, but that's okay. No, I'm not. This that I'm going to highlight, and this that I'm going to highlight are inverses of each other. Because this over here, which is y equals log base c of x, is the same as x equals c to the y. Same. And when you compare x equals c to the y to y equals c to the x, we've swapped x and y. This is not for the lazy thinker. And I'm not being insulting. I'm telling you, you need to be active in your brain here. Because I will be often talking about these two things on the right that are the same, but then I will be comparing them to the thing on the left, which are inverses. So what am I telling you? I am telling you that y equals 4 to the x and y equals the base 4 logarithm of x are inverses. But I've also told you that y equals 4 to the x is the same as writing x equal, I'm also telling you that y equals log base 4 of x is the same as x is equal to 4 to the y. These are just different ways of saying the same thing, which is the inverse of y equals 4 to the x. Again, this is not for the casual thinker. You're just going to sit there and go, yeah, I'll figure it out. No, you got to start figuring it out now. It's a totally new language. This is why some people struggle with logarithms. It's something new. You've been dealing with square roots and divided by for years. You've never seen a logarithm before. Same thing I feel as though I have to say. Textbook uses C, but your formula sheet uses B. So let's graph both y equals 2 to the x and its inverse on this set of axes. This is fairly straightforward. You should know that 2 to the x, so I'm going to be doing y equals 2 to the x with brown dots, and I'm going to be doing y equals log base 2 of x with blue dots. So you should know y equals 2 to the x. This was the very first lesson we learned. Has a y-intercept of 1, and every time x goes up by 1, y is doubled. So it will go from 1 to 2 to 4 to 8, etc. And I don't have room to double past 8. If I go in the other direction, y is cut in half. And we should know that there is a horizontal asymptote at y equals 0. Listen, if you swap x and y, just looking ahead, if you swap x and y to get log base 2 of x equals y, because it's an inverse, and the original function, which is in brown, has a horizontal asymptote, then the new function will have a vertical asymptote. Because we're swapping x and y, everything that's true about y becomes true about x. If the exponential function y equals 2 to the x has a horizontal asymptote on the x-axis, then the inverse will have a vertical asymptote on the y-axis. Which has an equation try that again. Okay, I'm still good. I'm not going to worry about trying to get the right color here for the box where it says log base 2 of x. I'm simply going to write here that the asymptote would be x equals 0. And now what I'm going to do very carefully is take this point, which is on the original function, which is at 0, 1, and I'm going to flip x and y because that's how we find an inverse. And it will be at 1, 0, which I hope makes sense to you that if the y-intercept of one function is 1, the x-intercept of the inverse will be 1. If I take this point, which is at, and you may need to write the numbers down to visually see them on paper, but this point right here is at 1, 2, and I swap the order of those numbers, I get 2, 1. 2, 1. Two, 4 is going to become 4, 2. 3, 8 is going to become 8, 3. Negative 1, a half will become a half, negative 1. And I think you're starting to see here how these are visually the inverses of each other because they have to be reflections in the line y equals x. So it's not perfect. I'm not going to try to fix that last point, missing the curve. This is what the two functions look like. I think I can kind of cheat a bit and maybe fix this one. There we go. So when we look at the exponential function, the y-intercept is y equals 1. I better put it as 0, 1. When we look at the logarithmic, there is no y-intercept. When we look at the exponential, there is no x-intercept, which explains why there's no y-intercept on the inverse. The x-intercept, though, on the logarithmic is at 1, 0. Domain of the original is x is any real number. When you look at the range of the logarithmic, it's y is any real number. This graph is going up and down. The second graph is going up and down forever. What is the range of the original? Y is greater than 0. And everything, by the way, in the box on the top left, we learned last week. If the range is y is greater than 0 on one function, then that becomes characteristically the domain of the inverse. I say characteristically because it's not y, it's x now. And that's it. All right. Now I'm going to go back to that bonjour, hello thing. And this is what the rest of the lesson focuses on. Question?
For y, you have I is equal to 0 for the asymptote, and x is equal to 0 for the asymptote.
So you're questioning what I wrote for the asymptotes?
Yes.
Okay. So this brown dotted line is the x-axis. Can you tell me what the y coordinate of this point is right here? What is the y coordinate of this point? What is the y coordinate here? Y equals 0 is the x-axis. This is something that popped up in the first unit when we talk about reflections across. A horizontal reflection is across the y-axis with an equation of x equals 0. It's something that you have to stop. This is a thinker too. It's not just saying, oh, it's the x-axis, x equals 0. You have to stop and think about what that means. Is that cleared up?
Yeah.
Okay. So this statement is all about bonjour and hello. And I want you to notice something here, that I have two statements. If I say, what is y equals c to the x, in logarithmic form, it's this. Those two things in blue are the same. They both have a base c. Y is by itself in the exponential, which means y becomes the argument in the logarithmic, and x is by itself. Sooner or later, you get lost in all this and you go, why is it that way? You know why this is true? Because somebody has said, let's rearrange this for y and let's use this to mean what y is. They've invented this language to mean that. On the other hand, I'm also saying, what if instead of having y equals c to the x, you had x equals c to the y? Well, then that can be written as y equals log base c of x. Listen, I don't have to use x's and y's. I'm saying these are equal. I'm saying these are equal. I'm saying these are equal. Give your brain a second to mentally digest that final statement there. One way or another, and it will work. Everybody will figure it out. You will have to figure out your own personal way of doing that. I mean, I could say, rearrange this for moose. Well, the argument in this exponential is moose. That's going to go by itself, and it's going to be that moose is the fish-based logarithm of duck. It doesn't matter what letters or words or symbols or expressions we choose. Admittedly, it's harder to say that than base 2 logarithm. It's the base fish logarithm of duck. So, write all of these in the other language. If n is equal to 4 raised to the p, that's an exponential description of the relationship between n and p. If n is equal to 4 to the p, how do we write that in logarithmic? Well, one thing I'm going to tell you in a few minutes is this statement, that a logarithm is an exponent. And the first time someone told me this, and it was years into my teaching, I didn't know what they meant, and they explained to me. I went, oh, that makes perfect sense. What a logarithm, and it's changed the way I teach this, what a logarithm is an exponent. What's the exponent up here? P, which means P is the logarithm. P is equal to the logarithm. The logarithm is the exponent. Over here, that means negative 5 is equal to log base 2 of 1 over 32. The base stays the same when you convert from one form to the other. It's just the argument of one becomes what the whole thing is equal to in the other. And by argument, when you look up here, everybody, P is the argument. And when you look here, N is the argument. Remember, the argument is the thing that you're operating on in mathematics. Root x has an argument of x. log base 10 of 100 is 2. Well, that means that the base of 10 raised to the exponent, why do I know 2 is the exponent? Because it's the logarithm. It's what the logarithm is equal to, will be equal to 100. When you have it in this form, I mean, most teachers would probably just say you take the base raised to the other side equals the argument. And that's fine. Quite frankly, I don't care how you convert bonjour to hello. I care that you understand when I say bonjour, you know I mean hello, and vice versa. That's right, isn't it? Is bonjour hello? Okay, good. This would be x to the m equals k. I was just joking. I knew it was right. I sense that there's something different on your handout. Alex.
4 log b times 9 is equal to 16. I said that wrong.
I have to see that.
It's a little different.
4 log base b of 9 equals 16. Okay. Okay. Forgot to change that one. So this is what it says. Is that right? Okay. You cannot convert a logarithmic expression to an exponential expression until you first write that. You have to rearrange for the logarithm first before you can convert it to exponential form. So if I divide both sides by 4, I end up with log base b of 9. And I want to go back to what you said, and it's not a criticism because this is really new. We would not say 4 log b 9 or 4 log b of 9. The proper way to say it is the base b logarithm of 9 or log base b of 9. There's a third way to say it, but I don't like it, so I won't say it to you. This is equal to 4. And now we can go b raised to the 4 is equal to 9. Any questions with 3? All right. What is log base b of 1? The answer to log base 2 of 1, or log base 0.5 of 1, or log base 10 of 1 is the same answer. So, what is a logarithm? A logarithm is an exponent. And in fact, I see that that's at the top of the page, isn't it? It says, so for some reason I've missed that page on here, but it doesn't matter. A logarithm is an exponent. So, I'm going to explain this in a couple of ways, and my hope is that it just becomes crystal clear at some point. When I look at that, I'm saying, what is this equal to? But if I change that statement to exponential form, it becomes this. Would you agree? So what exponent do I raise b to get 1? 0. And what I hope you get, this is the answer, is that you don't have to write this or this. You look at this and say, to what do I raise b to get 1? The answer is 0. To what do I raise b to get b? 1. And if you have to write, well, I want to figure out what this is, and it doesn't make sense to me, so I'm going to write it in the other language of b to the question mark equals b. Well, the bases are the same. The exponents must be the same. The answer is that question mark is 1. So the exponent is 1, but the logarithm is the exponent. Now C. What is, you have to listen to how I say it. What is log base b of b to the n? So if you start to get the hang of the fact that the logarithm is the exponent, then here's what C is asking you. And you need to listen and think about the words. To what do I raise b to get b to the n? Well, n. I raise b to the n to get b to the n. So this is equal to n. This is the answer. Now, if you wanted to say, well, I'm going to put a question mark here, and I'm going to write this in exponential form, you would write b raised to this question mark equals the argument b to the n. Oh, n is question mark. So the logarithm is equal to n. What is log base 2 of 64? So, I hope you're just saying to yourself, and if you're not, I hope you do soon, this is asking you, to what do you raise 2 to get 64? And that's a calculator thing, whether it's in your head or on paper. There's no algebraic way. I say on paper because I saw some of you doing, I think, Jay, you were doing like a factor tree on the quiz. Or you could do it on your calculator, but it's something that you just figure out. What is the exponent to which I raise 2 to get 64? Is it 6? So this is equal to 6. And your brain, sometimes I feel bad about putting this extra burden or pressure on you, but at this stage, you need to be able to figure that out. You need to look at that and go, to what do I raise 2 to get 64? Now, if that is a burden that you cannot handle, then I suppose you could call that x and write it in exponential form, but then you're doing stuff we learned yesterday. Do you agree you could solve this with a common base? Do you agree by doing this, it's really unnecessary, because if you know 2 to the 6 is 64, you know x is 64. All right. I am curious to know how many of you know what log base 6 of 1 over 36 is. Do you, Ashira?
So it would be 6 raised to something, and that something would be -2.
It's -2. So this is -2. And this is certainly one that I think many people will benefit by writing. I'm going to choose question mark here this time instead of an x. That the base of 6 raised to the question mark is 1 over 36. And 36 is 6 squared, and 1 over 6 squared is 6 to the -2, so the exponent that makes it work is -2. And you're not always simply going to be able to say, to what exponent do I raise the base to get the argument, oh, 6. It's not always going to be that easy. For example, and I'm curious, Ashira, I'm going to stick with you. Do you know what log base 8 of 2 is? What is it?
So it would be 8 raised to something equals 2, and that something would be 1 over 3.
Right. So now I'm going to write this out and ask you a further question. And I'm sticking with you because I think other people are learning a lot as we go through this procedure that you're using. You're saying this is equal to something that I want to find, so 8 to the something equals 2. But now my next question to you is, do you just know it's a third because it's the cube root of 8? Okay, so there's that possibility that you just know I need to take the cube root of 8 to get 2, and the cube root is an exponent of a third. Or you could say that 8 is 2 cubed and work towards a common base and end up with 2 raised to the 3 times question mark equals 2 raised to the 1. So 3 times the thing we're trying to find is 1. It's 1/3. And these little, I call them chippy examples. They're very basic examples. I don't care how you get the answers. You're going to see later on that we use this for more grand things. Okay? So this is equal to a third. All right, example number 5, when the base of a logarithm is not specified, it means base 10. So if you just see log 8, it means log base 10. So we're asked to determine what this is. Well, let's call it, oh, heck, let's call it A for answer. By the way, how many of you understand this is equal to 4? Because it's saying, to what do I raise 10 to get 10,000, which is a 1 followed by 4 zeros. So you can write this as 10 to the A equals 10,000. And I really don't believe that you need to write it out as a common base to see that it's 4. Because as soon as you go, oh, it's base 10, you're already answering the question, aren't you? You're going, well, what exponent do I put on 10 to get 10,000? Well, that's 4. I mean, I don't think you do this and then the light bulb goes off and you go, oh, A equals 4. Maybe it does. The answer is 4. How many of you see that the answer to the next one is negative 3? Okay. Because this is saying it's a base 10 logarithm. 10 raised to whatever this is 0.001, which is 1 over 1,000, which is 10 to the negative 3. So this is equal to negative 3. I changed my lesson and I retyped it up here. Can you check that 6A is the same thing you have? I think I might have brackets on your handout as opposed to times. Okay. So determine f to the negative 1 of x, which means the inverse. And it doesn't mean an exponent of negative 1. That's that goofy notation from lesson 1, or unit 1. First thing, write everything with a y. This is the same function. We haven't found the inverse. Now we're going to find the inverse by swapping x and y and getting 5 multiplied by 3 to the y, then plus 4. And now we have to rearrange for y, which you couldn't do before today. So what am I going to do here? I'm going to subtract 4 from both sides. Then I'm going to divide everything by 5. And I could have written, 1/5 bracket x minus 4. I could have written 1/5 x minus 4/5. I'm going to leave it like that. We're just about done. Now you have to write what y is equal to. Well, y is the base 3 logarithm of x minus 4 over 5. And by the way, when you write logarithms, it's never too late. I should have mentioned it earlier. You want that base to be written so it's clearly a subscript, right? There's really 3 lines of written work in logarithms. There's the main line where you would see the word log and maybe part of the argument. There's a lower line where you see the subscripts. And then if you have exponents, they're in the upper line. That's it. This is y equals 2 log base 3 of x plus 4. So the inverse, we swap x and y. Keep doing that. We swap x and y to get this. So x and y have just switched places, that's all. Now I rearrange for y. Well, I can divide both sides by 2 and get log base 3 of y plus 4. So if it were y plus 4 squared, you'd take the square root. But it's the log of that. So what's the opposite operation of logarithms? It's exponential. So this will be 3 to the x minus x over 2 equals y plus 4. We're just doing the bonjour hello thing at this point. And then I can subtract 4. And get the answer. Any questions with either A or B of example, what I think is 6? You're all turning the pages, so I'm guessing not. Now a bunch of chippy little things, and these are all different. What is the value of x? How many of you can look at that and tell me the value of x? It's 3. But, and here's my advice to you, if you're ever looking at a logarithmic expression or equation, and you don't know what it means, translate it to the other language. So if I do this, I get 3 to the x equals 27. Well, again, I don't think we need to algebraically show our work here. We know 3 cubed is 27, or you should know 3 cubed is 27. We'll see, Reese. This one's a little more tricky. And I think some of you can tell me that it's equal to a third, but many of you will need to write it out in exponential form. You would write 27 to the x equals 3. And if you're like Ashira remembers from Math 20, and many of you will as well, that a cube root is an exponent of a third. And I need to take the cube root of 27 to get 3, so the exponent is a third. If you don't remember that, you would change the 27 to 3 cubed, and then you can write a common base equation of 3 to the 3x equals 3 to the 1, and that means that the exponent of 3x and the exponent of 1 are equal, so you get x equals a third. How many of you know what the answer to this is? I'll give you a second to just think about what it's saying. And I hope, and I'm willing to bet a large sum of money, that everybody in the room, if I ask you to think about what that means, you're imagining it in exponential form. I hope. I don't know how else you would do it. You're saying that 4 is the exponent that I stack on x to get 81, so x is equal to 3. Now I have a question for you. How many of you see that it's 3 because you know 3 to the 4 is 81? Okay. What if it was that? What would you do here? When you write x to the 4 equals 810, which it's not, what do you mathematically do to get x? Fourth root, right? If it was x squared, you'd take the square root. In other words, x will be equal to 810 to the quarter. And it's interesting, and I want you to think about this, that I can get rid of that exponent not by thinking of roots, but by saying I'm going to raise both sides to the quarter. Because x to the 4 to the quarter is x to whatever 4 times a quarter is, which is 1. 1. So it's 3. Alex, do you know what this is?
125.
125. Because when you think of it in exponential form, it's 5 cubed equals x. Well, this is grade 7 math, or 6, I don't know. 5 times 5 times 5 is 125. This whole lesson, I mean, it's about the exponential and logarithmic being inverses, and we looked at those graphs. But it's mostly about you thinking of these expressions that are logarithmic in a particular way. 1/2 to the x equals 32 means 1/2. Well, do you see what I just did there? I meant to say log base 1/2 of 32 equals x, and what came out of my mouth? X to the half, or 1/2 to the x equals 32. I can't help myself but read it that way. Well, common base would be 2. This is 2 to the 5. 1/2 is 2 to the -1. So a power of a power, we multiply the exponents. Negative x equals 5, so x equals -5. That's it, I think. Yes? Okay. This is not a really long lesson, but we did learn a lot today. We had a quiz in there. You still have some time left, not a lot, unfortunately, but this is about mainly this, but also knowing that these two are inverses of each other. This is the thrust of the lesson. Okay. The written response is due Friday. I'll get your quizzes marked and back to you by tomorrow. Written response is due Friday. It's looking like your unit exam will probably be next Thursday. Okay.